Have you ever wondered how machine learning can predict whether an email is spam or not? Or how we can predict the likelihood of a patient having diabetes? Well, these are what we call classification problems. For these problems, we will look to a widely used machine learning technique called Logistic Regression. In the last video, we saw a machine learning technique called Linear Regression. This technique could give us a model that predicts continuous values, like the price of a car, for example, which can be any value within a given range. For example, the price can be $40,206.7. However, in contrast to regression problems, classification problems deal with discrete values. For example, whether an email is spam or no spam. So this problem has two possible solutions. Either it's true or it's false. Either it's 1 or it's 0. Either it's in the positive class or it's in the negative class. These are all possible ways to describe the outcome. But overall, we prefer to use the values 0 and 1. 0 is used to express that it's false, and 1 is used to express that it's true. And as you might have noticed, we speak of a positive and a negative class. Indeed, that's why it's called a classification problem. The outcome belongs to a certain class. And to solve these problems, we won't be using linear regression. Instead, we will be using another widely used machine learning technique called logistic regression. We will explain logistic regression using an example. Let's assume you want to predict whether a patient is sick or not. Then we'll say if y is equal to 0, the patient is not sick. And when y is equal to 1, the patient is sick. If we now look at a certain data set where we plot whether a person is sick in function of the age of the person, then we might find a plot like this, where you have some people that aren't sick and some people that are sick. Now, I want to show you why using linear regression isn't a good idea. If we were to use linear regression, we could say, let's predict that a person is sick if our hypothesis is equal to or higher than 0.5. The problem, however, is that linear regression is sensitive to outliers. This outlier will make sure that the hypothesis will be shifted more to the right, and so if we now look at our predictions, we see that we classify these patients as not sick, while in fact they are sick. Another problem with linear regression in classification tasks is that our prediction can be greater than 1, which makes it difficult to interpret. What does it mean if we get a hypothesis of 1.4 if we only have two possible classes, namely 0 and 1? And finally, linear regression assumes a linear relationship between the input features and the output, and it may fail to capture the nonlinear relationships inherent in many classification tasks, as we will see later. So, ultimately, we would like a model that gives us predictions between 0 and 1, that is robust to outliers and that can handle nonlinearities in our data. That's why we won't be using a straight line as our hypothesis. Instead, we will use the Sigmoid function, also called the logistic function, and it looks as follows. This function squashes any input into a range between 0 and 1. In simple terms, it helps us convert a linear combination of input features into probabilities. If we now substitute the value z with theta transpose times x, we get the hypothesis we will be using in logistic regression. And this is exactly what we want. All predictions will be between 0 and 1, the hypothesis is robust to outliers, and now our predictions will have a meaningful value. Namely, the value of the hypothesis will now give us the probability that y is equal to 1. To get a better understanding of this, let's look to an example. Assume that you have a data set like this and you want to create a model that predicts whether a person is sick based on their age. Then you run an algorithm, like gradient descent for example, to find good values for the parameters theta that fit the data well. And once this is done, you can put these values into the sigmoid function, which will give us our hypothesis. Now, this hypothesis might output the value of 0.7 for a certain age. What this means is that the person has a 70% chance of being sick. So, the hypothesis gives us a probability that y is equal to 1 given x parameterized by theta. And now that we got the probability of the person being sick, we also know the probability of the person not being sick, which in this case is 30%. Now that our hypothesis tells us what the probability is that the input belongs to the positive class, it will make way more sense to say let's use the point h is equal to 0.5 to decide whether an input belongs to the positive or the negative class. So now we will let the model predict that y is equal to 1 if the hypothesis is greater than or equal to 0.5. Or in other words, if the probability is greater than or equal to 50%. And if our hypothesis outputs a value lower than 0.5, we will predict that y is equal to 0. So this point, h equal to 0.5, is helping us to decide in which class we can place the example. It's as if this point creates a boundary between the positive and the negative class. And indeed, if we could plot h equal to 0.5, we get a line separating both cases. That's why we will call this the decision boundary. Note that h equal to 0.5 is the same as saying that theta transpose times x is equal to 0. So in other words, we can also say we predict y equal to 1 if theta transpose times x is larger than or equal to 0. And we predict y equal to 0 if this term is smaller than 0. To get a better intuition of what this decision boundary looks like, let's look at the following example. In a later video, we will see how we can obtain the optimal parameters theta with the use of gradient descent. But for now, let's assume that if we try to fit the parameters through the data, we get the following values for theta. We can now put them in our hypothesis and voila, our model is complete. So, like we just said, we will get the decision boundary if we set our hypothesis equal to 0.5. Or in other words, if we set theta transpose times x equal to 0. If we do this for our hypothesis, we will get the function x1 plus x2 is equal to 5. And this function is what we call our decision boundary. If we were to plot it, we would get a straight line, clearly separating the positive from the negative class. Now we will predict y is equal to 1 for all the points that are equal to or greater than this decision boundary. And we predict y equal to 0 for all points that are beneath this line. Let us look to a second example. But now, let's assume we got the dataset like this. In this case, a straight line won't do the job. A straight line is not able to separate the positive and the negative class. I suggest you pause the video for a second and think of a way how we could solve this. Yes, indeed, if you have seen this video on our channel, you know we could solve this with adding polynomial features. If we add some higher order polynomial features, we can capture the nonlinearities in our data. Now, we could for example get these values for theta, which will give us the following decision boundary. And if we add even more polynomial features, we can even capture more complex shapes. I know, this probably is a bit overwhelming. Which features should we use and which polynomial terms should we add? But don't worry, later on we will see how we can automatically choose these parameters. But for now, let's quickly summarize what we have seen so far. So checking if an email is spam or not, or estimating if a patient is sick or not, are all examples of classification problems. In fact, you're not even limited to the value true or false. You can make your own classes, and you're not even limited to the amount of classes. You can even make more than 2 classes. You can extend this model to multiple classes, also called multi-class classification. For example, if you want to analyze images to be either a car, a bike, a pedestrian, or something else, you can make 4 classes and assign to each class a discrete value to work with. For example, an image of a car is y equal to 0, a bike is y equal to 1, a pedestrian is y equal to 2, and y equal to 3 tells us that it's something else. This multi-class classification is something we will see later on, and we will see that this won't be much harder than working with only 2 classes. So if you don't want to miss this, I recommend that you subscribe to the channel. Now back to the summary. These classification problems we can solve with logistic regression, which has a hypothesis that looks as follows. This hypothesis is based on the sigmoid function, and it tells us the probability that y is equal to 1 given x parameterized by theta. We have seen that if we set our hypothesis equal to 0.5, we get a decision boundary. And everything that is greater than or equal to this line, we predict to be y equal to 1. And every example that outputs a value lower than 0.5, we predict that y is equal to 0. Next, we'll see how we can automatically choose the right values for the parameters theta. But before we do this, we must look at a concept we call the cost function. If you have any questions so far, please leave them in the comment section below.